Hello everyone, welcome back to Last Call BBS is the name of this game, and we're going to do Chipwizard Professional. I forget if it's been one video or two, but at some point it was like, build a latch, and I was like, I don't remember how to do that. So I took a break. And I went and looked up do we actually want a latch or a flip-flop? And I'm like, yeah, we do want a latch, that's what I thought. And also, like, what the heck a latch is. Or like, right? A latch is kind of a low-level circuit building block, the simplest kind of circular reference, I guess you could build in a circuit where your output is not determined strictly by your inputs, but by some loop that you've built in the circuit, so that the previous state can feed back information to the next state. And to build this latch, all we need is two NOR gates and the routing ability to send them to each other. Now, I assume one of these puzzles before was like, hey, build a NOR gate. But, like, it's impossible to know from looking at these things, right? And or a not. Yeah, I mean, so, like, we could build or and we could put a not on it. That's fine. But was there something more clever? Because we don't have that much space, right? I don't think any of these were NOR gates. What was safety interlock? That was one that has the alarm that's like if they're both high, then it so I don't think so. But a motion controller. Okay, so the idea is you take two NOR gates and for each one you feed each of them one of the signals from the left, one of your two input signals, set and reset basically is what we have here. This puzzle is calling them on and off, but the traditional names are set and reset. So each NOR gate has one of those as input and has the output of the other NOR gate as its other input. And when you do that, you wind up with something that remembers which signal was pressed most recently. Now, wait a minute. That's not quite... Well, okay. Typically, in a NOR gate, it is drawn showing both outputs. Because you have two... Sorry, not a NOR gate. In a latch, you have two outputs, right? The output of each NOR gate. And one of them represents, yes, the thing should be high. The other represents, no, it should be low. We only need one of those as our output, but we do need the other one anyway to feed back to the input of the other. So, all right, if we were going to build a NOR gate, just like not worrying too much about space yet, what would that look like? If I wanted to say, so NOR is not OR, so signal only if both of them are false, right? So that's what a NOR gate looks like in this universe, right? Where, well, okay, obviously the other end has to be wired up to high, but yes. So if either one of these is true, then the output of this will be false, and otherwise it'll be true. And that's what NOR means, not, neither of them should be true. So we just need two of these and appropriate routing between them, and then we should be set, right? It's not like the routing is trivial or anything, I think. I don't have any, oh man, okay. So, which one do we need to wire to the output? It's the one that is connected to off, right? Because off will be inverted on its way out. And so if off is high, then this thing will definitely be outputting low. Yeah, okay. it seems like tempting. I don't know if it actually like fits, but it seems kind of pretty, I think, to have like those are capacitors. To have this be the overall layout of the circuit. Because then they're so close to each other. Wait. Can we do a better NOR? I ask because this routing is going to be hard. Getting, like, you know, each of these needs one input. One end of these red things to connect to one of the blue things on the other one. And that's not hard. That's pretty easy, I think. But just like you need more connectivity from this, right? Like let's say we do that. Then we kind of have to do that. But then how is this getting any signal at all, right? Well, okay, I guess it doesn't have to be symmetrical. We could do this if we had to. It's not clear yet whether that solves any problems, but you could do it. Actually, maybe this is the way to go for both of them. That might make the routing simpler somehow. Problem is, like, there's a lot, I guess, right? How do we get this routed all the way back here, and this routed back here, or maybe the other way around, I'm not sure which, while also getting plus V routed to the other two red terminals we haven't wired up yet? There's a plus V here. That one's not bad. Or here. Let's maybe think first about how to route power through this whole thing, just in case that turns out to be interesting. Like, I mean, there's this, right? That would get us power up here pretty easily. Or here. Maybe I can just shift this whole thing up a bit. Yeah, maybe that's an idea. Then, let's see. Then it's pretty easy to get like this over that, for example. Although I don't want it over both of them, do I? How about just there? Plus V can go this way. And we can route the other input in like that. Why do I have two vias on this? Oh no, this is wrong. On on is supposed to go to the blue end of this, isn't it? No, that's off. Off is going here. Okay, so we're saying, I guess, on isn't supposed to go to this at all. Because it's getting the off signal. Okay, I guess I should actually figure out. I want the one that has off wired to it to be the one over here, if possible. Because it's easy to route this way, I think. But maybe it's not so bad to go this way either. So this has off as an input, voltage as another input, and this needs to come from over here, right? So we can do that like this. Voltage is the other side of this thing. Well, wait a minute. No, this is bad. Because now I made the output of this thing like down here? And it's going to be a nightmare to route over there, isn't it? Wouldn't it be better if its output were this side? No, right, no, because the way I've wired it up, I need this one to get off if I'm going to wire it to the output here, right? Right now I'm wiring here, so maybe we can do that. Oops. So this is a pretty nice setup, I think. It's not taking up too much space around it. It leaves this thing fairly open to contact from elsewhere. And its output is here, which is not too hard to get this way, I think, because that's what I want. No. I want the output of this one to go over here. So this thing's output just needs to get to there, right? Might be best to just switch to blue silicon as fast as possible. Like that. So that this can use the metal layer to get over here, which I think is where it wants to go. So this needs to get fed off, which is easy enough. In fact, we can even point it the other way now. This wants some voltage. And then I think we're just routing this up to the motor output. So does this make sense? This is getting positive voltage. This circuit is being disabled if either on or this thing's output is high. So that makes this the R part of the latch. The R signal is coming out of here. We're feeding R into this. We're also feeding off into this, which makes this the S part of the latch. It's going to the motor. This looks right. Instability, I see. I have to throw capacitors in here somewhere? Well, that's not too surprising. We need a clock sort of thing somewhere. So let's see. I think we just want them in between both of the loopbacks, here to here and here to here. And that's easy enough to do. I mean, maybe I'm wrong. Maybe you have to do something else. But we have space for them pretty easily if that is what you're supposed to do. Very close. The problem is that the motor starts out high. Well, I mean, I think I understand why that is. So let's look at how things are in the first time step. At first, everything was low. And then no buttons were pressed. I guess that's the issue, is an SR latch's behavior is not really defined if you haven't fed anything to it yet, and this requires us to define it. Now, I mean, okay, so a traditional SR latch also includes an enable signal, which says whether to do something. I still don't think that would help us here, because even if we set enable to low at the beginning, it still just has sort of an arbitrary starting state. Now, obviously, a thing we could do at a sort of high level would be I think let's look at the outputs of our two things actually right now. So this one, which represents S, is emitting high right now, which is bad. What is R emitting right now? That's this one. Or no. This is S. On represents S, right? Set. And this is reset. But what is the output of this? This is this is when S is low. It should be on. And I mean, right now S is low and it's not on yet because of this capacitor. What if I just took out this one capacitor? That doesn't seem like very scientific, and I can't imagine it's right, but like, what if we did it anyway? I see. So this was enough to introduce some delay between the two circuits. And we didn't need it to be a balanced delay. We just needed there not to be a short circuit sort of like race between them. Okay, and I think we can improve the layout of this quite substantially, right? This whole thing looks like it could easily be scooted up without really any routing problems. And that would save us this whole row. It almost seems like I could save this. But I don't know if I actually could without a bigger redesign. Because we're using this space for a capacitor right now. And that's kind of the only convenient space in between these two. Because you can't have a capacitor and silicon in the same place. What does the select tool even do? You can just kind of scoot stuff up, huh? I don't understand how to, I don't understand how to do anything now that I've selected it, though. I can't drag it. Is it just saying you can't drag it because it would conflict with something else? Okay, I could do that. That's not what I want. Can I copy this whole thing? Oh my god, select is so bad. Copy? Paste? No. All right, I'm not going to worry about it. Obviously, we could move this, but I don't want to stress out about it. The tools are not helping. So what do you think? Do we want to do another one of these? Programmable delay? Interesting. Alarm should activate n cycles after the run input. And you get to choose what n is by which time signal you send. We don't ever have to deal with them sending multiple time signals. Okay. And they also never set the time signal and run at the same time. So we get a moment to wait while the run signal is chosen. Oh, although it does mean if it means they're turning off. Wait, what happens when they here, right? They turn off the run signal, and instantly the alarm goes back off. I see. So that's fine, I think. Huh. Do they always hold the time signals for long enough that the alarm turns on before turning off run? I guess so. Okay. So we don't have to like remember the time input, which seems dreadfully hard. And we also don't have to worry about none of the time inputs being high. So we can just sort of pretend if we've checked 3 and 5, then we can assume, and they're both low, we can assume 8 is high, basically, which seems sort of nice. It seems like we need several routes from run to alarm, right? Can probably even put these up here. So we go like that. And then if time 3 is high, we're allowed to jump straight over to run. So something like that, right? Probably want to do it that way. God, where am I going to fit in another one of these and a bunch more capacitors? Maybe I should be running stuff through here. And then whether or not run was high, we can throw in some more capacitors here. And this is an alternate path that you have to get to alarm. But it's enabled only if... Well, okay, and then let's throw in 3 more capacitors, shall we? So this is the last chance path that's always enabled. You can always go this way without needing any silicon bounces. But you can also take a shortcut after just 5 if time 5 was high, right? And time 8 we don't need at all. That's the joke here. So what do we think of this? If time 3 is high, then when run becomes high, we'll get 3 bits of warm up and then whoop, straight over to alarm. We'll also be treating this as a directional loop back to this side, but that's fine. We don't care. Um, because this will be blocking the signal anyway. If time 5 is high, we go through here. We fail to go through here. Go through here. Jump over. This seems fine. Yeah. I'm a little bit surprised that I wasn't in one of the normal, like, obvious solutions here. I guess, like, apparently people either found a way to cut out 2 columns or a way to cut out no columns. That's interesting. Is there something I could learn there? I'm almost cutting out this column, I guess. I could move this in here. How do I get time 5 in, then? Oh. Well, okay. I could move these 3 capacitors over to the right. I thought I was going to need more space around here, but I ended up not routing that way. And if I did that, then this could move up. And that seems like it could be very good. But then I wouldn't be able to flip this anymore because it would be poking into a capacitor, right? So if I just flipped it as is, then it doesn't seem possible to route from here Wait, I don't have to route from here to here, right? I just have to route from here to run? As long as it doesn't go through any capacitors, which kind of means it has to go through here, right? Yeah. All right, I'm gonna leave it alone. I have not really pressed for optimizations in this game, and when there's one that looks easy, I'm happy to take it. That one I looked at it for a while, didn't seem easy. What's a synchrony detector? Should be high when in A and in B both transition from low to high in the same cycle. So, I mean, it's a little flip-floppy, right? Because flip-flops are like edge transition versions of latches. But here we don't have a specific signal, which is the one we're trying to remember. We want to check both like the previous and the current state. Okay, so an alarm only goes high for a single cycle. Yeah. I mean, we obviously can't fit 2 latches in this thing. It's insane. There's no way there's enough space. So we can't just have a latch for A and a latch for B and look at the A and B inputs as well as the latch outputs, right? So when... I guess we can just use a capacitor to view the past, right? The problem that the capacitor has with viewing the past is like if something goes from high to low, you detect that instantly. So it's not really a faithful look one step in the past machine. But we don't need that here. Do we? We just need to know we need, if it was low last signal. No. If it was high last turn, to disable the output we would otherwise be making. And whether it's low this turn or low last turn doesn't really matter. The difference between those two doesn't matter. So we kind of need 2 transistors, each with sort of 3 inputs and 1 output. No, we don't even need that, do we? We need a 2 input and a 3 input. If A and B are both if A and B are both currently high, well, and let's put capacitors here. So these represent what they were recently. Now, we'll arbitrarily choose A as the kind of primary thing here. So can't use this space, can I? It's hard to avoid, like, cross over the capacitor itself too soon. Well, we don't have to structure it that way. We don't have to see are A and B high now, and then see, okay, in the past were they both low. We have basically if you want, you could say that we have a single piece of silicon with 4 inputs. Where no, but it's hard, right? Because you want to invert the sense of things. Because past inputs should force the output low, current inputs should force the output high. But we don't have to get these two to cross over and talk in the present and then double check the past. We can compute from in B, like both its current and past state. Like, are those both? Because really what we want is we want to make 4 Boolean assertions, right? Is in A high? And is in A in the past low? And is in B high? And is in B in the past low? We don't need to do those in any specific order. We just have to combine them all at some point. So I think something that would be quite reasonable would be to take B and combine it with itself, right? So something like that. Except I can't have a via here. Like that. Now we've done one of our 3 computations. And its output is here. Then we could say, do the same thing up here. And then these two just want to combine in kind of the natural way. I guess we should try to save on, don't use both of these rows, right? So, let's do a sanity check before we hit play. Do we think this is going to work? If A is high and in the past A was not high, this goes through. If B is high and in the past B was not high, this goes through. So this input and this input are whether A and B are both correct from at all time frames we care about. By the way, I think we can improve by moving this down a peg. And then this just says, are both of those things true? If so, go ahead. So, yeah, that seems right. And yeah, indeed, this is higher than it might need to be, which we can fix. What do you have to say? Moral accounting. I'll be honest, it felt pretty amazing to get a program that normally costs thousands of dollars handed to me on a disc for the equivalent of a couple bucks. Now, it's not like I cost the developer an actual sale. If the program hadn't been available to me this way, I never would have used it at all. Obviously, I wasn't going to use it to make designs I was going to sell or anything. I know this kind of stuff gets touchy, though. Anyway, that's what things were like back then. My understanding is that when everything went networked, most of these businesses shut down. I didn't even know you could minimize that. That's fine. So, but this 12, huh? 12 is a bit better than I can do, I think. Is it? I think I was planning to get a 16 by squeezing this in down here. Right? If I move the capacitor to there, then I can just take this and move it down left a bit without affecting anything. Right? Yeah. Oh, also this isn't 16, it's 20. I mean, sure. I don't even know what the heck we would do to improve this. Well, okay, here's something we can say for certain. The people who are doing it in 12 can't possibly be using 3 separate transistors, right? Because that takes up 12 space already, and you also need at least 2 capacitors somewhere. So they must be doing what I kind of thought would be hard to route, where... But I don't even know. How do you do that? I don't think you can have a single loop of silicon that just has 4 things interrupting it. Or not loop, arch. Because like I said, you need... Wait a minute. Okay, this might be interesting to explore. In a previous puzzle, we tried sneaking around some of the constraints a bit by not bothering with an OR gate and just like welding together two of the inputs with metal and then having, oh look, the result of this is, the metal. It is whether either of them was high, and that worked. We got the right output, but we drove the inputs high when we weren't supposed to. Here, we have a capacitor blocking, and so, like, I still think it doesn't work. If they ever hold the input high for, like, 2 ticks, which I assume they do, then we would be driving an input unexpectedly. Yeah. I thought we could maybe quickly combine, like, old A and old B into old of either A or B, basically, by just, like, gluing them together with metal. But that's going to drive the A and B inputs, which is unwanted. I thought it would be a nice way. We could save a lot of transistors that way, right? Because then we would only need one big transistor that would be carrying basically like whether that combined input was right as its like long way, a blue one, and then have the current A and current B interrupted as reds to allow it to flow through or not. But I don't think you can do that. Because it would mean driving the inputs, at least the way I have it imagined. Huh. I mean, we could even confirm that real quick, right? I'm imagining attaching these to each other. Now, obviously, this is not going to compute the right answer, but I want to confirm that this will end up driving. It'll give us errors in the A and B parts of the signal, right? Yeah, see? This is not allowed. Oh, that was the wrong thing to delete. Okay, well, that's fine, I guess. I think we're probably not going to do another puzzle here today, but let's go look at what the next... Oh, and/or combo. Okay, fine. Ooh, a switch debouncer. Maybe I'll just try some Dungeons and Diagrams. That always puts me right to sleep. And I was in the middle of one yesterday, wasn't I? Yeah, I got this far. Incredible. Well... Okay, this one that goes through a treasure is kind of interesting, isn't it? It means we know the exit to the treasure room lies along that column. Because... otherwise, we would have to draw a wall like somewhere below it and somewhere above it. You know, if it were like this, for example. Which is impossible. But I don't know what to do with that information. I don't have enough high numbers here. Man. I know that one of these two is open, and the other one is a wall, which means that one of these has all opens except for this space that's next to this monster, and the other one doesn't. But I don't know what to do with that. We can get rid of this text here. Well, okay, the fact that The fact that we know the only wall in this column is one of the boundaries of the treasure room tells us that any place that can't be part of the treasure room wall must be open along this column, right? So this, for example, is open. And the same thing is true here, because we know the exit is not along this row. Oh, and I guess we know the treasure room extends this far for some reason. I don't remember how I proved this. Maybe it's incorrect. Since I did that last time, not this time. But we know this can't... Okay, anyway, so anything that can't be part of a treasure room must be open. A treasure room wall must be open. So the treasure room could extend this far, which means this could be a wall. Ah, it couldn't. Because there's only room for one wall in this column, and there would have to be two. So this can't be treasure room wall, which means it can't be wall at all, so it's open. And the furthest right we could reach would be this, so this is open as well. I bet we're going to find the same thing about this square, huh? Yeah, because if this were the exit to the treasure... well... Right, because the highest the treasure room can extend is here. And there can't be a wall here. Can there? Maybe. Well, no, because if there were, it would have to be a wall that's not part of the treasure room, which means the treasure room would have to be beneath it. I don't know. Yeah, of course. If the highest the treasure room could be would be like this, which obviously is impossible. But if we put a wall here, then we wouldn't have room for the rest of the treasure room walls. And if this isn't a treasure room wall, it can't be any other kind of wall. In fact, we could ask, I think, can the treasure room reach up here at all? I think the answer is no. Oh, that's how I had this marked before. I had said, could the treasure room extend all the way out here? No, because then there would be too many walls in this column. So that has to be part of the treasure room. And you can ask the same question here. Could the treasure room extend all the way up into this row? No, there would be too many walls up there. So this is part of the treasure room, which means we have finally a 2x2 that's part of a treasure room. Still not really getting anywhere, though. Well, okay, there's only one wall in these places, and it can't be like here or here, right? Because there'd be a dead end in the corner. And this can't be open, I think, right? Because if it were, this would either have to be a wall. Oh, that's fine. Did I mean to say this can't be a wall? I think it could be either. This could be open. This can't be a wall in that case, but it could be open, and that's fine. If this were open, this would have to be the only wall. It's a little bit hard to believe. But I don't immediately see a disproof, so we'll just leave both of these as they are. And over here, isn't something similar going on? There's only one wall. It can't be this space, because that would be a dead end. Can't be this space, because that would be a dead end. And likewise here. Now this row is almost, or this column's almost good, right? There have to be 4 walls out of the 5 remaining open spaces. There's only room for 1 more open there, right? I'm not sure that does enough. Ah, wait, could this be open? I don't think it could. Because then this would have to be closed, but so would this. So that's a wall. Okay, I mean, not a huge surprise. We kind of thought it might be. But it's nice to have a solid proof of an actual wall somewhere. How about this? Is that in a similar problem? Not really. Yes, it would make... Oh, hang on. Now that we have a wall here, we can say this can't be a wall because it would be a dead end. And that gives us this whole monster's set up. This can't be a wall, obviously. This has to go straight. This has to be a wall because if it were open, this square would have a problem. This looks kind of interesting. Oh, there's only room for 1 more wall in this entire column. And even if we stretched down the treasure room to here, we would still need 2 more walls here because we know the exit can't be along this column. So this has to be part of the treasure room. We're getting somewhere this time, at least. Slow going. There's only room for 1 more non-wall here, I guess. So it looks promising to say that it has to be the wall of the treasure room. But I don't think that's necessarily true. Oh, hang on. Now that we know this is part of the treasure room, we know the treasure room can't go any further down. And we already knew it couldn't go any further right. So it has to go further up. And now we know that the exit to the treasure room is along this column. So we can wall off the treasure room on all other columns. Like that. And that's fantastic information, right? That's like everything. It's all coming together. There we go. Okay, getting this monster solved suddenly solved everything. Cool. Well, we made it in just under an hour. As long as I'm fast. Hope you guys enjoyed. Thanks for watching. I'll see you next time. Bye.